Hi, good morning, good afternoon, good evening, class. This is Mr. Arocena, and on today's video, we're going to be talking about standard solutions first, and followed by titration curves. So we talked about titrations in a previous lesson, which is basically mostly about math and how to use stoichiometry to help solve acid-base titration problems. Today, we will talk about titration curves and kind of what titration curves are and what they mean. But first, standard solutions. So a standard solution is basically any solution that you know with an accurate, or you know the concentration of to a very accurate degree. Standard solutions are used in titrations because, as we mentioned in the titration lesson, we need one of the solutions to be a very known quantity. Now, standard solutions tend to come in two varieties. The first are known as primary standards, and then the second type is a standard made from a primary standard. Primary standards are usually very unreactive and very stable compounds. So once you make them, they're not just gonna randomly react with the air and become something else. So they're very stable, very pure. The other type of standard is basically we use a primary standard and then we titrate it to calculate its exact concentration using the primary standard. We tend to use in the lab, for at least our classes, I tend to use these types of standards because they're usually easy to make. Okay, and then from there, that's where we do all of our titrations. Now, the most common standard solutions that you see in a chemistry lab for acids and bases are actually not strong acids or strong bases. The first is potassium hydrogen phthalate, and then the other one is oxalic acid dihydrate. These are two common acidic primary standards. For us, I tend to use hydrochloric acid, standard hydrochloric acid, as my acidic primary standard. It's actually not a good standard to use because if left sitting for too long, the hydrochloric acid does tend to sort of lose concentration if not stored properly. But as long as we make it up and use it up within the same lab period, it's usually not too bad. For bases, the common basic primary standard is sodium carbonate. Sodium carbonate is a very stable compound, so in solution it's actually quite stable and quite long-lived. Again, though in our lab, I tend to use sodium hydroxide as a standard for bases. Again, like hydrochloric acid, sodium hydroxide does not have an infinite shelf life, so if we don't use it up quickly, the concentration does actually change slightly over time. Now, titration curves are basically what you would get if you graphed the pH versus concentration during a titration. And there are three types of titration curves we'll look at today. The first is strong acid, strong base titration. These are the easiest to understand because strong acid, strong base, the strong acid will basically create equivalent amount of hydronium, and then the strong base you can basically just reduce to some concentration of hydroxide. And most often what will happen is when you have the strong acid plus the base, you end up getting your salt and then water, like that. And it's pretty much usually a 1-to-1 ratio, and the stoichiometry is relatively easy. The other type of titration curve we'll look at will be weak acid and strong base titrations, and then weak base with strong acid titrations. You can do weak acid, weak base titrations, but because of the way that their equilibriums are set up, those calculations are a little too complicated for us at the moment. Okay, so these are the three we'll look at. Alright, so strong acid with strong base titrations are, I think, relatively easy to work with because of the way that strong acids and strong bases work, and that the leveling effect basically reduces strong acids to an equivalent amount of hydronium, so we really only need to worry about that, and then strong bases are reduced to an equivalent amount of hydroxide. Now, because of this, the equivalence point, so the point where you have equal amounts of hydronium and hydroxide, this will occur very quickly, and you get this very sharp rise of pH. So during this portion here, during this portion here, all of your H3O plus will combine with OH minus, and that happens as long as you have excess amounts of hydronium. Eventually, when it equals out, you'll have equal amounts of this, and that'll happen at the equivalence point. This is usually where we stop the titration. Any extra bit of hydroxide after that ends up pushing it into the base side, so here you get just base. So this is why the pH rises sharply during a strong acid, strong base titration, because for the first little bit, you've got a concentration of hydronium being neutralized by hydroxide. So the concentration of hydronium drops as you add more hydroxide. Eventually, you have an equal amount of each, so you get this equivalence point, and then any extra hydroxide will push it into a higher pH. Now, because of this, for strong acid, strong base titrations, the equivalence point will usually be around pH 7. That kind of makes sense because you're going to end up neutralizing, when you neutralize all of the hydronium, you basically have a neutral solution, so the equivalence point will be at pH 7. When we're doing a strong acid, strong base titration, the indicator we choose needs to change around pH 7. And if you recall from our indicator lesson, one of the more common indicators we use is phenolphthalein, but phenolphthalein actually changes color to pH higher than 8. So phenolphthalein is actually a really bad indicator for strong acid, strong base titrations because its color change occurs well past the equivalence point of pH 7. Alright, now the other type of titration, the weak acid, strong base titration, this one acts slightly differently. And that's because of the nature of the weak acid. So here, you have this situation here where the pH doesn't change much. So pH is relatively steady here. And the reason for that is because if you recall, a weak acid will only partially dissociate into its conjugate base and hydronium form. So it creates this equilibrium. Now, if I add a hydroxide to this, so if I'm adding a strong base, which is hydroxide, what will happen is that this H3O plus concentration will start to go down, because that will react with the hydroxide to create water. Whoops, there's no plus there. There you go. So the hydroxide will react, or the hydronium will react with the hydroxide to create water. I guess 2 water molecules. But as this hydroxide concentration drops, what will happen is this equilibrium will shift forward to replace it. So any hydronium that gets used up by the strong base gets replaced by the weak acid equilibrium moving forward. So EQ shifts to make more hydronium. So in effect, any hydroxide I add to this equilibrium doesn't actually do anything, because if I add any hydroxide, it removes the hydronium, but then the equilibrium will shift forward to remake that hydronium. So this is why the change is very slow at first. Okay. Eventually, if I add enough hydroxide, then all of the weak acid will eventually disappear, and then that's where you get this sharp rise here. As a result of this, the equivalence point ends up being at a pH above 7, because you end up adding quite a bit of hydroxide. And as a result of this equilibrium shifting forward, you actually create more of this weak base, and this weak base will push the equivalence, or will push the pH above 7. So, to reiterate this, so during this portion here, you have your weak acid. It's going to react with the water to create a conjugate weak base, and hydronium. When we add the strong acid to this, these two will react to create water. I guess 2 waters. Now, as this reaction occurs, So as the hydronium concentration goes down because it's reacting with a strong base, this equilibrium will shift this way to remake the hydronium. And this shifting of equilibriums is what makes the change of very, very slow. It basically maintains this pH until all of this gets used up. Once all of the weak acid gets used up, then you see the sharp increase in pH. Now, the reason that the equivalence point is above pH 7 is because once all of this is used up, you have a lot of this which can react with the water to create some amount of hydroxide, which is usually pretty small, and then DHA, like so. So the reason it's above pH 7 is because as this equilibrium shifts forward, we're creating more of this conjugate base, which will create some amount of hydroxide, which makes the equivalence point actually slightly higher than pH 7. Now, an important quantity here you might have noticed is this half equivalence point. This half equivalence point is basically just the half the volume that's needed to get to the equivalence point. So if the equivalence point was at, say, so let's make an example. So if equivalence point occurs after, say, 100 milliliters, then the half equivalence point is 50 milliliters. That's all the half equivalence point is. Okay. The half equivalence point actually kind of matters later on, and we'll talk about that when we get to the examples. With this type of calculation, with this type of titration, we can use this to calculate the Ka of the weak acid. It turns out that the Ka of the weak acid ends up being equivalent to the concentration of hydronium at the equivalence point. And then from this, we can actually calculate the concentration of the original weak acid. So if we are trying to figure out the concentration of a weak acid, we can use its equivalence point, and we can use the fact that the equivalent point occurs, or sorry, the Ka occurs at the half equivalence point. And then we can use that to figure out the concentration of the weak acid. So if we're dealing with an unknown weak acid and we need to know its concentration, we can use this to figure out kind of what the original concentration was. To do this, we simply set up another rice table to help us along with this calculation. Alright, so we set up the rice table as follows. We'll write a standard weak acid reaction. So weak acid plus water will create some amount of conjugate base, and then it's hydronium. So we'll just sort this out. So our weak acid is the unknown concentration. We'll set this up as an unknown. This part we don't care about. We have none of this, none of this. We'll go plus x, and this will be minus x. But since this change is usually pretty small, this will just end up being the same. Now the x ends up being the concentration of hydronium before any of the base is added. So let's just go backwards. So this portion here, we can get this from initial pH. So the problem will usually tell you what the initial pH of the weak acid is. And because of that, we know then that the concentration of hydronium is equal to the 10 to the negative pH, like that. Okay. So this ends up being 10 to the negative pH. 10 to the negative pH, like so. Then, if we know the Ka for that particular weak acid, that'll allow us to calculate this, because we know that Ka is equal to concentration of A minus times concentration of hydronium divided by original concentration of our substance. Right, so reminder again that the x in that rice table was the concentration obtained from the initial pH, and we can then set up the Ka equation like so, and then we can rearrange that and solve for the concentration of our weak acid. Alright, so now in summary, for weak acid and strong base, we get the following. The pH at the equivalence point will be greater than 7, and this is due to presence of conjugate base. The presence of the conjugate base makes the solution slightly basic after equivalence. The Ka can be found from the concentration of hydronium at the half equivalence point. And we can recall then that the HA can be found by simply rearranging our Ka equation like so. So that's our summary for weak acid and strong base titrations. Now for weak base strong acid titrations, it's kind of the same, only a little backwards. So the titration curve is basically flipped on its head. So here you have a relatively steady section here where you have your weak base plus water, and this will create an equilibrium with that'll create a conjugate weak acid and hydroxide. Now, as you add a strong acid, so if I add a strong acid to this, it will then create water in a very similar fashion to the weak acid strong base curve. Now, as the hydroxide concentration decreases, this equilibrium will shift forward to recreate the hydroxide. So here you have a relatively slow change of pH, because again the equilibrium shift. Eventually, once all of this runs out, then you get this massive drop in pH, and your equivalence point will be here. So for weak base strong acid titrations, it's basically kind of the opposite of the weak acid strong base titration. As such, the pH at the equivalence point will be less than 7, and that's because of the presence of the conjugate acid. So the conjugate acid makes a solution slightly acidic. Now, with this, we can calculate the Kb in a very similar fashion to calculating the Ka. The only difference is that rather than using concentration of hydroxide at the equivalence point, half equivalence point, we use instead of using the concentration of hydronium at the half equivalence point, we use the concentration of hydroxide at the half equivalence point. Okay. And then with this value, we can then calculate the concentration of the weak base. Right, so the process of calculating Kb is very similar. We simply have to set up a rice table for the weak base, and then this table will look like this. So base plus water will create conjugate weak acid and hydroxide, and then we'll end up with the following. In a very similar fashion, get some unknown. This doesn't matter because it's water. 0, 0, plus x, plus x. This is minus x, but really it's the same. And then this ends up being x and x. Now, the x is the concentration of hydronium before any acid is added to this situation. So this number here, this is the concentration of hydroxide at initial pH. So this really becomes, not initial pH, initial pOH, because it's a hydroxide. So this becomes 10 to the negative pOH. And this is 10 to the negative pOH because they're kind of the same. And then you can calculate the concentration of the base using this equation here. And recalling that the Kb comes from the concentration of the hydroxide at the half equivalence point. So even if you don't know what the Kb of the weak base is, because it's not known weak base, if you know when the half equivalence point occurs, you can measure the pOH at the half equivalence point and then calculate the concentration of hydroxide, which ends up being the Kb. And then with that Kb, you can then use the Rice table as set up here to calculate for the initial concentration of the of our weak base. Okay. So in summary, for weak base strong acid titrations, we get the following. pH will be at an equivalence less than 7, and this is due to conjugate acid, because the weak base will create a conjugate acid. We can find the Kb from the concentration of OH at the half equivalence point. And this is really, again, 10 to the negative POH. So we can measure that at the half equivalence point. And then we can find the concentration of the original weak acid or weak base using this equation here. So let's go through an example of doing all of this. So we're going to determine the Ka and initial concentration of a weak acid. So this is a weak acid strong base titration. We need some information, so we need the original volume of the weak acid. We need the volume of the strong base we're using. And we need two pH values. We have our initial pH of HA, and we have the pH at the 14 point. So this is our half equivalence point, half EQ point. So this is all the information we need. So if we were to do this titration in class, we would basically do the exact same thing. We would measure out some known volume of our weak acid. We would then titrate to the equivalence point using a strong base. We would measure the pH before the titration, and then we would measure the pH at the half equivalence point. Alright, so first step is we're going to calculate the Ka. So Ka is the concentration of hydronium at the half equivalence point. And we can do this by doing the following. We can take 10 to the negative pH, which is negative 4.6. Entering that into our calculator, this gives us a concentration of hydronium of about 2.51 times 10 to the negative. Alright, so there's our Ka. I'm going to skip the Rice table a little bit because we know then that at pH 3.5, the concentration of hydronium is going to be 10 to the negative 3.5. So this is 0.00032. But we also know that the concentration of its conjugate weak acid is also the same because of how the Rice table works. And then therefore, we can then calculate Ka as follows. Concentration of hydronium times concentration of A minus divided by the concentration of the original weak acid. We know Kb from previous calculation is that. We know the concentrations of H3O plus and A minus is that. So we can simply rearrange the equation to solve for HA. So HA, so concentration of my weak acid will then be 0.00032 squared, because there's two of them, divided by 2.51 times 10 to the negative 5. 2.51 times 10 to the negative 5. And putting that in our calculator, we get the following. We get a concentration of 3.98 times 10 to the negative 3. Or I guess with two significant figures, 4.0 times 10 to the negative 3. And there's the concentration of our weak acid. Alright, so to summarize, the strong acid, strong base titration, so strong acid, strong base, we get pH, equivalence point is at around pH 7. And this one is no weird Rice tables to really worry about. It's a straight up 1 hydronium plus 1 OH minus will neutralize to water. So no equilibrium table necessary. Weak acid strong base titrations, the equivalence point will be at equivalence point pH will be greater than 7. You can calculate the Ka is equivalent to the concentration of hydronium at the half equivalence point. And you can then rearrange the Ka equation. So you can rearrange the equilibrium equation of Ka to find Ha. And then the reminder here, I'll just highlight this one here. This is at initial pH. And that's the important distinction. A lot of students will make the mistake of using the pH at the half equivalence point, but we don't need that. When calculating the original concentration of the weak acid, we use the initial pH for the concentration of hydronium. And then for the other one, the third type, which we did not do an example of, but it's really the same as the previous one, we just swap some values around. So weak base, strong acid, the equivalence point will be at pH less than 7. We calculate Kb as the concentration of hydroxide at the half equivalence point. And we can use the Kb equation to calculate the original concentration of our weak base. And again, noting that this concentration of OH is at initial, I'll make a note, POH. Okay. Oh, and the final thing to note is that because of the way the equilibrium works, the concentration of H3O plus is the same as the concentration of A minus. And also make a note here that the concentration of OH minus is equivalent to the concentration of HA. And then you can go back and look and see the proof of that using the Rice table. Alright, so your assignment then for this is basically just putting all these calculations into practice. They will be as follows. If you need any more assistance or there's something that doesn't quite make sense, you guys all know how to contact me.